Okay, so one more example that I'm going to show you all of triple integrals. We've seen a bunch of examples, different kinds of solids that, different points of view on how to do the slicing, and, you have to get a feel for this kind of thing. And one more example I think will be helpful. So here we have a region that's bounded by 5 given planes. So z equals 0, z equals x, z equals 2 minus x, y equals 0, y equals 3 minus z. What in the world are we going to do to draw these planes and figure out what the intersection of these 5 planes is? The first thought you might be thinking is, well, I guess I'll draw the one plane, and then I'll draw the other plane, and I'll draw this other plane, and this next plane's going to and then that you're going to have to sort of visualize all 5 of the planes together, see in your mind's eye how they fit, and then draw the picture. Right? And that's not how this one's going to work. I don't think I could do that without having already known the answer. Okay. So there is something special about these planes that we're going to capitalize on. If these were just random generic planes, golly, it'd be hard. Here's the special thing I want to point out. These first 3 planes. It's not terribly hard to notice. The equations of these first 3 planes listed, there's no y's in there. Right? Now, what does that tell us? The fact there's no y's in those equations. Different ways you can think about it. Sort of most directly, you can observe that means that these planes, if you've got a point in one of these planes, you can change the y-coordinate willy-nilly. And it doesn't take the point out of the plane, right? Change the y-coordinate whatever you want. If z is equal to 0 and you change that y-coordinate dramatically, okay, z is still 0. Likewise for all the other equations there. So what that means is these planes are all parallel to the y-axis. Right? You change the y-coordinate, so what? If you want to take a chapter 1 approach to this, which is perfectly fine, you can observe that because there are no y's, these equations all have this form, and then that their normal vector has a second component, which is 0. Right? If the second component is equal to 0, well, that means that that normal vector is parallel to the xz plane, which means that the plane itself is parallel to the y-axis. Right, so same result, sort of different point of view. Okay, so what we're going to do then, I'm going to draw these 3 planes first. They're all parallel to the y-axis. That means that I can understand them simply based on how do they, I want to do different colors, how do they intersect in the xz plane, and then, well, just kind of drag along the y-axis. So, for example, the plane z equals x. Well, let's look at the line z equals x inside of the xz plane. That's what z equals x looks like in there. The plane has to contain that line. And, oh, by the way, don't forget, this plane, parallel to the y-axis, that means that this is that plane. So, likewise, for z equals 0, right? And for x plus z equals, what was it, 2? Yeah, x plus z equals 2. So, altogether, we have these 3 planes, and it's pretty easy to see how those planes relate to each other. They're all parallel to the same line. They make what we call a triangular cylinder. Everybody on board with that? So this is a very valuable first step when you notice something, a shared feature of some of the surfaces that you're interested in. Try to find some way to capitalize on it. So that's what we did here. Okay. So now, what do we do about that? What do we do about the remaining? These remaining, notice I've got solved for y. This says y equals 0. So I'm going to think in terms of, inside of this triangular cylinder. I'm going to try to think of the remaining surfaces as giving y as functions of x and z. And that'll help me understand how to, figure out where, there's going to be one remaining plane maybe over there and another remaining plane over there. And if y is a function of x and z, then you can sort of see how they fit in like that. So the first one is y equals 0. Y equals 0 is going to slice through that triangular cylinder like that. And then lastly, y is equal to 3 minus z. Okay, now this one's going to be a little bit weird. Y is equal to 3 minus z. Quick observation, no x's. This plane's parallel to the x-axis. So I'm going to understand this plane by thinking about what it looks like in the yz plane and then dragging it parallel to the x-axis, because I know the plane that I'm looking for is parallel to the x-axis. So what does y equals 3 minus z, what does that look like over here in the yz plane? Well, y plus z is 3, so that gives me a line kind of like that, sitting inside the yz plane. I want to visualize what happens when I drag that parallel to the x-axis. Right, and then having done that, I would like to ask, how does this plane then cut through this green triangular cylinder? And this is just a geometric appeal, but it's gonna intersect maybe there and there. Notice that this plane is kind of leaning to the left, right? So where it intersects on the base, because it's leaning to the left, it's going to intersect this top ridge further to the left, because it's sort of leaning that way. So it's going to intersect the top ridge, maybe over here like there or something. And so that intersection is going to be something more like that. Okay, so this is a pretty, I guess we're technically not quite done yet, so let's go ahead and finish this off before I look back. We've got all 5 planes drawn. I've got these 3 first green planes defining this triangular cylinder. Then I've got the remaining 2 planes showing how they cut through that cylinder. And the solid that I'm looking for is the solid's bounded by these 5 planes. And that solid is this thing here. Okay, and let's try to clean up a little bit, something like that. Actually, you know what? Maybe I will leave that there. Let me just come down to where I've drawn a better picture already. Here. Okay, so we've put in a bunch of time just trying to figure out what this thing looks like. But finally, at least we have a picture of it. And now let's remind ourselves of the question. The question was, how can I rewrite a triple integral over this region as an iterated integral, nested integral? Okay. Alrighty, so here we are again. We gotta look at our solid and think about different ways to slice, our different slicing options. For each slicing that we take, we've gotta figure out bounds, and bounds correspond to points. Points are on surfaces. Surfaces have equations. It's the usual game, right? But we do have to decide which order we're gonna slice. Now, this is a tricky example. What's tricky about this is you really do have to be very careful about which order you slice. I'm going to show you a couple of different options and what goes wrong with them. And in fact, there's only one good first choice of variable to slice with. So let's start by slicing perpendicular to the x-axis, just for, alphabetical reasons. So we're slicing perpendicular to the x-axis. Our slices are going to look kind of like this, for a while anyway. Okay. And here's the problem. In so doing, eventually you will slice through that, I'm going to call it a corner. It's an edge, right? But it's kind of a corner in this. That's where two surfaces intersect. And so we're going to have a problem when we hit that. Problem being that these slices that we were taking, the upper edges of the slices were on that back plane for a while, but after we get past that red corner, they have jumped to a different, I need to, blue. They have jumped over to a different plane. Right, that's what the slices look like way over here. And their upper edges are on the front plane of the triangular cylinder, not the back plane. Okay, everybody see the problem? So we can see the writings on the wall with this choice. If you do your DX slices on the outside, down the road as you go and slicing inward, you're going to have different formulas for different bounds on the inside integrals because, look, there are different planes defining what those bounds are. So that's a bad choice. Everybody on board? Okay. So you can see, now I drew a picture here for that purpose, but I'd like to point out that you don't have to draw a complicated picture to make this realization. You can just kind of think to yourself, all right, mentally, what does it look like if you take such a thing and start slicing perpendicular to the x-axis? Oh, look, I'm going to hit this corner. Okay, let's not do that. Okay. So likewise, now let's consider what happens if you start by slicing perpendicular to the y-axis. Well, they start off just fine and dandy. Here's what our slices look like. For a while, until you hit that corner. And then your slices start to look a little bit different. Right? They're not triangles anymore. Now they're tetrahedrons. Tetrahedra? No, what do they call it? No, sorry, trapezoids. Sorry, trapezoids. So again, problem. Now, y goes from, here to here. You can probably find those bounds, but you're gonna have to break it at this point because the inner bounds for these blue cross sections will have different formulas than the inner bounds for these green cross sections. So again, the simple way to see this, again, you don't really have to draw the picture. You can see pretty easily that as you slice perpendicular to that y-axis, you're going to hit a corner. Corners are bad. Don't do it. Right? If you can possibly avoid it. So last option, alphabetically that is, slicing perpendicular to the z-axis. Come on, I can do better than that. And your slices look like this the whole way up. No corners, no problem. Everybody happy? So that's the big point I wanted to make. Now there's details to work out as to exactly what are the bounds. Your z bounds are going to be based on this being the first z slice. That's the last z slice. So pick a couple of points. You might say that first z slice is defined by that point. What's the z coordinate of that point? The last z slice, maybe this point. What do you know about that point? So those points are on what surfaces? Those surfaces have what equations? Write down the algebra, solve. It's at this point, it's all the same kind of a process, so I won't go through those details. But we have our slicing, our first slice anyway, decided. I guess I will make one last observation, and that is that this z slice like this, what choice should we make as to which way we slice next? Should we slice this green slice, this z slice? Should I slice perpendicular to the x-axis, or should I slice perpendicular to the y-axis? Well, good news, this is a rectangle. And so it kind of doesn't matter, right? You can do dx, dy on the inside or dy, dx on the inside. It doesn't matter. The important point is that because of the geometry of the shape, the z had better be on the outside. Okay, questions? How are we doing? Details are worked out on this example, by the way. Here's what it ends up being. Okay. All right, so moving along, a bunch of examples for y'all to work out. Just a reminder, I did thin this out somewhat. Yeah.
So just wondering, if you slice first, like with respect to z here, and the z ends up on the outside.
Yep, that's what I suggest. Yeah.
I don't know. Just so when you slice first with respect to z, it doesn't end up like right on the inside of the like dz dx dy.
What I mean by first, so here we have the terminology problem, right? So specifically what I'm suggesting is that we slice with the differentials in an order like this, and so this is what I'm calling z first, because as part of the slicing process, the one that's on the outside is the first in the slicing process, right? So when you go through your slicing, you're defining your nested integral from the outside in, right? So it's first from the slicing point of view. It's last from the evaluate the integrals point of view. We evaluate the integrals inside out, right? And it's also last in terms of notationally, I guess. But what I mean by first in the process, as I was describing the slicing, I meant first as part of the slicing. Yeah. So perhaps what I should have said, we've got to do our dz on the outside. Yeah. Good question. Anybody else?
And then, so when you're solving for dx next, you just use the bounds.
Yeah, that's right. So we've got to look at, we're gonna fix a value of z somewhere between 0 and 1, and then for that z slice at some value of z between 0 and 1, we're going to ask what's the range of values of x. And on the picture, here we go, we're fixing z at some value between 0 and 1. Let's say there. Right? And on that z slice, I'd like to know what is the range of values of x. Well, our x slices, if we slice perpendicular to the x-axis, geometric appeal, those slices of the z slice will look kind of like this, right? And so our first slice is this, and I'm going to pick this point arbitrarily to look at. Our last slice is this, and again I'm going to arbitrarily pick that point to look at. So our question comes down to, what do I know about these 2 points? And well, these 2 points are on certain planes, right? This point right here, it's on the left face, if you will. It's on the back face, if you will, and it's on the z slice. Write down those equations, solve for x. Yeah. So the familiar process, in other words. Yeah. Okay. All right. Okay, so we're going to move along to, just a quick reminder. I emailed and suggested that, maybe y'all should wait on number 9 until we've had this conversation that we just had. And the idea is, I'll just point out for your consideration, notice those first 3 equations have something in common. And how can you capitalize on that? How can you turn that to your advantage? So, very similar to what we just discussed. Okay, moving along. Talking about change of variables. Change of variables is an extremely powerful tool in computing integrals. It's not a new kind of integral. It's a tool for computing them. So let me just remind you where we are in terms of our development of integrals. I've made references back to single variable integrals. Y'all know those. Cool. Double integrals, so a second kind. Triple integrals, our third kind. These are all different kinds of integrals. Change of variables is an approach for how to compute these things. It is not itself a different kind of integral. So here's the big idea. Sometimes your domain stinks. Right? Sometimes you don't like your domain. Sometimes your domain has corners all over it or something. Right? Or it's algebraically awkward and it makes your bounds have square roots and arctans and other, undesirable stuff in the bounds. So if that's the case, if you have a domain with if you have an integral with an undesirable domain, wouldn't it be nice if you could rewrite the integral over a different domain? Wouldn't that be super? Now, obviously, you can't just change the domain. You might have to make some sort of modifications to the integrand. I mean, because, look, you've got to play fair, right? You can't just say, I don't like this domain, I'm going to use this domain over here instead, right? This is, in fact, exactly what's going to turn out to happen. We're going to find that if you don't like your domain, then under certain circumstances, you can change it to a different, much nicer domain, and your life becomes much easier. Okay, I want to point out that we've kind of already done this before in a way, at least part of what I just said. We have seen a theorem where an integral on one domain gets rewritten as an integral over a different domain. And here it is. It's the substitution rule for integrals. Right, very often you think of the substitution rule as a tool for anti-differentiation, and that's fine. Sure, arguably that's the easiest way to think about the substitution rule. But you could write down a substitution rule for integrals, and this is it. And I presume y'all have probably seen this before. So let me zoom in on this a little bit. So this formula here says that what's going on here? There we go. Okay, it's fine. If you have an integral from a to b, then you can rewrite that as an integral from g of a to g of b. Oh, okay, now you got to be careful with that because, well, yes, you do have to, note that this integrand is not the same as that integrand. These are conspicuously different. In fact, if anything, if x is g of t, then really that is equal to that, and so here's the actual change that we're making to the integrand, other than plugging in x equals g of t. We're introducing a new factor into the integrand in the form of g prime. So there's that. So that's the modification that we make. So now I know you all have seen this result before. I know you've probably proved this result before. It's not hard to prove using the chain rule and the fundamental theorem of calculus. Pretty straightforward. If you're not sure how to do that, come talk to me in office hours. I'll be happy to show you. No big deal. Okay. What I want to do for you, though, is I want to give you a different point of view on this. And look, you've probably noticed the pattern. Very often when I take an old topic and give you a different point of view, it's because that different point of view is setting up the opportunity to extend to the multivariable setting. That's exactly what I'm going to do here. I'm going to take a point of view on the substitution rule that will allow me to extend it to the multivariable context. And that's exactly what we're going to do. By the way, when we get to change of variables, it's going to be the substitution rule in multivariable integrals. Okay. So here's the idea. We're going to view this function that was just an algebraic device here. Right? This was kind of, algebraically speaking, if I were to say x is g of t, then algebra, scribble, and then I can rewrite this as that, right? But I would like to view this a little bit more geometrically. I'm going to think of g as a function where there's a t-axis and there's an x-axis, and let's look at it. And here it is. There's a t-axis, there's an x-axis, and g is a function from one to the other. And notice, innocent observation, if you have an interval from a to b on the t-axis, those numbers, if you plug into this function g, if x is g of t, then that means that these numbers that come out are the interval from g of a to g of b. Yeah, but I'm making a little assumption here, by the way, just for convenience. And it turns out that it doesn't really technically matter, but makes life simpler. I'm going to assume that g is monotonically increasing. If it doubles back on itself, it creates annoyances that are that can be dealt with, but I don't want to get bogged down. Okay, so you can kind of start to see this coming, that here's the interval from a to b, here's the interval from g of a to g of b. What we're talking about is an integral defined here as relating to an integral defined here. Okay, now let's start chopping. We know that we're going to do the way we create integrals is we take intervals and we chop them up. So let's take this interval from A to B and chop, chop, chop like we always do. Right? And unsurprisingly, I'm going to call these the places where I chop, I'm going to call them T0, T1, T2, T3, etc. Okay. Well, each one of these points can be put straight into that G function, and out come G of T0, G of T1, G of T2, etc. Okay. All right? Everybody happy? Now, we chopped these. We did this chopping over here for the purposes of creating a Riemann sum. Riemann sums, as we've defined them so far, all had this characteristic of convenience that I chop evenly. Now let's take a moment to reflect on why did we chop evenly. It's because we're lazy, right? It's because it was convenient. It makes my life simple to be able to say, oh, well, the distance between these is B minus A over N. What a nice, tidy little formula. And it's uniform, it's always the same, right? It's just to make things easy. Now let's ask a different question. Yeah, but did we really have to do that? Why, in fact, were we chopping things up in the first place? And the reason we were chopping things up in the first place is we had some question to ask. We're defining an integral on the interval from A to B. We're computing the mass of something or an area or whatever, and it was a hard problem. And if we chop it up into smaller pieces, on the smaller pieces, it's an easy problem. That's the only reason we're chopping, right? There's nothing really actually that important about these pieces all being the same size, right? In fact, if you look at an advanced calculus textbook, what they call a real analysis book, the most sophisticated definitions that are given for Riemann integrals do not require that they be evenly spaced, because they don't need to. There's really no need for it. Okay. All right. So I make that observation because even if I were, carefully, methodically slicing of even widths over here, when I stick these values into the G function and look at what comes out over here, these are clearly not going to be evenly spaced unless that G function just happens to be really, really boring, like, linear or something. Those G's you would not expect to be evenly spaced. And so, per my comments seconds ago, it doesn't matter, though. Right? I can still think of this as I'm taking this large interval, which is too big for me to make, simple arguments like, mass equals density times length. But when I chop it up into little pieces, even though this piece isn't quite as little as that one, they're still getting littler. In the limit, they all get arbitrarily little. Right? And it's okay. And it's still the case that I can define an integral on this domain to be a summation over these not equally spaced little subintervals. Okay. All right. How are we doing on that? Is everybody okay with that part? Okay. All right. Okay, so what we're going to do now is we're going to consider an integral on this domain over here. Integral from G of A to G of B. This is on the x-axis, you notice. So, integral of f of x dx. This integral that I have written down here, we have a definition of integrals. It's a Riemann sum. Now notice here I put a little subscript down here that says delta xi. I am by this notation indicating that I recognize that these little delta x's are now not necessarily all the same, right? But again, it doesn't matter. Don't worry, that's fine. We're still adding up over all these little pieces. We're adding up integrand times size. Each one of these pieces, we're writing down, density times length. It's still going to give us little pieces of mass. Each one of these is a little piece of, again, let's say mass. If you add up a bunch of little pieces of mass, you get the total mass. That's it. The argument still makes sense. Okay. All right. Okay. So what we're going to do now is we're going to think about this integral. This is an integral you'll notice on this blue integral, g of a to g of b, some integrand f. We're on the x-axis, so we're looking at the integral of f of x dx. And I'm going to ask, can I rewrite this integral instead as an integral that takes place over here? So here's how that works. First observation I want to make is that if I look at this little piece of the domain over there on the t-axis, and if I look at its image, this little piece over here on the x-axis, if I look at the function that relates them, g, we are currently in chapter 5, but let's think back to chapter 4. From the chapter 4 point of view, what's going on here? We have here, you might say, a little displacement along the t-axis. This little subinterval represents a change in the value of t. This little subinterval over here represents a change in the output values of the g function. So here we have a change in what's going into g, a change in what's going out of g. And what is it that relates input changes to output changes? Well, the derivative of the function that connects them. Right? So g prime of t is what you multiply by delta t to get delta x. I'm going to take in that point of view. I write that down right here. G prime is what you multiply by delta t to get delta x. Approximately, of course. And in the limit, all that goes away. Okay, so we're actually ready to do it now. Here we're going to make the switch. Here is our integral on the x-axis, just as a reminder. Our integral on the x-axis is from g of a to g of b. Definition of an integral, no big deal. Minor asterisk, these are non-equally spaced subintervals. Again, who cares? Doesn't matter. Well, we just agreed that delta x is g prime times delta t. Right? And from the original setup of the question, xi is g of ti. So all I'm really doing here is plugging in to turn that integral, namely that Riemann sum, into this expression here. Everybody happy? So just plugged in. Everything that's written up here in terms of x, I'm rewriting it in terms of t. And conveniently, g does that for me, right? G is the function that tells, oh, you have x's? Okay, here's what x's are, all in terms of t. X is g of t. All right, so the very last step, not that much to this very last step. This is just a matter of moving parentheses around. The parentheses, you'll notice, were like this, around what that delta x was. I am now going to just regroup a little bit, innocently. I'm going to regroup like this. All right, let's do the parentheses like that instead. It's just moving parentheses around, perfectly legal. Right? But now let's look at what we have. This, as I've got it written here, with my parentheses conveniently moved, I am adding up something times width on the t-axis. Right? The values that I'm plugging into this expression, I've got this expression here, f of g multiplied by g prime. The values that I'm plugging in there are these values ti. These are the endpoints of the subintervals after slicing on the t-axis. This, which I rewrote over here, just for cosmetic purposes, this is the exact same as that. This is exactly, character for character, the Riemann sum definition of a new integral. This is the integral from a to b of f of g of t, g prime of t, dt. And so, in fact, we have shown that x integral is equal to this t integral. Said differently, this integral from g of a to g of b is equal to this integral from a to b. Different domains, yet these integrals are always equal. Is everybody on board? Okay. So a certain amount of details, but big picture. Let's go back up here and think about large scale, geometrically what happened. We have this function g that takes t to x. We started with an integral defined over here. I'm just going to say integral dx. We started with this integral on the x-axis, and by capitalizing on this function, I rewrote that as instead an integral over here dt. Right? That's what happened. Started with this, played algebraic games, ended up with this. And I think it's important to point out that arrow seems to go backwards. Right? Hey, wait a minute, doesn't G go that way? Well, G does go that way. Numbers that you put into G, you put in a number on the left, it turns into a number on the right. Right? But that's not what we're dealing with. What we're dealing with here is an algebraic expression. Algebraic expressions go the other way. If you give me an x, if you give me this expression called x, I can rewrite that x. That's an algebraic expression over here. I can just say, hey, by the way, x is g of t. Now all of a sudden I'm over here and I'm writing things in terms of t. Right? So the simple act of plugging in x equals g of t takes algebraic expressions from the right to the left. It's a little counterintuitive. You have to just kind of just stare at it and digest and accept that, yeah, sure enough, it's weird, but that's how it works. That's what the action of plugging in takes algebraic expressions backwards through the function. So this is called a pullback. I'm going to use that term a lot, a pullback. The idea of a pullback is that if you have a function going one way, then expressions that are written in the target, expressions pull back to be expressions in the domain. All right. The other observation I'll make, I've got to switch over to the other observation, here's our punchline, by the way, that we just wrote down. The other observation I'll make is about, algebraically, what's the cost of trading this domain for this domain. And the cost it's pretty easy to identify right here in the picture, but f of x, you got to plug in, you got to rewrite x as g of t, but that's not really a cost. That's just write it in terms of the variable that you want to do business with. It's not really doing anything. The cost is in this g prime. This g prime right here. That's the extra factor that you have to stick in. This is what represents how much the little width dt gets stretched out to become the different sized width on the x-axis, dx. This, you might say, is the factor by which you stretch this piece of domain into that piece of domain. And because this is the factor by which you stretch to turn this into that, I like to call this the stretching factor. All right. So that's a big way to think about the substitution rule that we've sort of re-derived here. The substitution rule can be thought of as a pullback accompanied by the appropriate stretching factor. How are we doing? Is everybody happy? Okay. All right. So I spent a bunch of time talking about single variable calculus stuff that y'all already know. Again, to set the stage, to take the point of view that adapts appropriately. So that is what we're going to do now. I'm going to do the same thing in a different context. Here we are in a multivariable context, and this is not going to look like the substitution rule. It's going to look pretty different. But it's going to be strategically the same as this point of view that we just took on the substitution rule. So here we have a domain in the XY plane. Let me observe, by the way, real quick, that this is a really bad domain. I mean, really bad. There's corners everywhere. No, I mean, think of it in terms of your slicing options. If you were going to slice this up, there's a corner here that you kind of hit as you're going. If you're slicing first perpendicular to the y-axis, you're going to hit that corner, but then you're going to next hit this corner, and then you're next going to hit this corner, and so 4 separate chunks, right? I'm going to have to. That's yikes, highly undesirable. Then you say, okay, so let's slice a different way. Okay, well, yeah. But if you slice perpendicular to the x-axis, you kind of sideswipe that edge, which means you've got a chunk there and a chunk there. And then you're going to hit that corner, which means you have a third chunk there and then a fourth chunk there. Either way you slice this, dx, dy, or dy, dx, you're going to have 4 separate integrals. This is undesirable. Okay, so we have an undesirable domain. We're going to try to rip off. I keep forgetting I'm on a different. We're going to try to rip off the strategy that we took here. The strategy that we took here ultimately started off with let's view this domain as being the image of this domain. And because the green domain is an image, I can pull an integral back to the pre-image. All right, so let's see if we can do that over here. Let's say that we can, and the details of how to do this, we'll talk about this a little bit later. A little bit later today, very soon. But I'm going to take our undesirable domain and let's presume that I can find a way to view that as the image of this more desirable domain over here. And if we can pull this off, this is a huge win. Huge win. Because this domain this was going to be 4 separate chunks. If I can pull the integral back over to here, then I'll have an integral on, Colorado. Right? Easily sliced, constant bounds. This is everyone's, dream double integral domain. Best case scenario. All right. Now, again, so you may ask, how do you figure out what this is? Right? That's a separate conversation. We'll talk about that in a few minutes. Okay. Right now we're going to assume we have it. Okay, well, here we go. We've got this new domain over here on the left, and let's slice it up. And we'll just, slice up this whole thing here, etc. That slicing, well, just like we did in the case of the substitution rule, let's draw what those slices turn into. Likewise this way. Oh man, that's no good. Something like that. Right? And one way or the other, all the slices that I make over here turn into slices over here, the resulting little pieces, subdomains. I call them sub-rectangles over here, but their images over here aren't rectangles, right? But these little pieces have as their images these little pieces. And if I want to do the pullback, it's a two-step process. One thing I'm going to have to do is everywhere I see x and y, again, if I have an integral defined on this green domain, everywhere I see an x and a y, I've got to plug in what those are in terms of u and v. That's the first part of the pullback. Is just plugging in x and y are known. Right? G is known functions of u and v. So plug in. Sure. The sticky point is that size, this little piece of area. I want to focus now on this little piece of area right here. This little piece of area is presumably not the same as the little piece of area that it came from. Right? This G function, somehow or another, is going to take this little blue area and it's going to stretch it out in some way to make this highly different little piece of green area there. So we just need to figure out a stretching factor. Once we figure out our stretching factor, we are home free and we can do the complete pullback of the integral on the xy domain into an integral on the uv domain. So what's that stretching factor? Okay. This picture has a problem in that it's good to see the overview, but now I need to really focus on this little teeny weeny little rectangle and this little teeny weeny little. By the way, kind of parallelogram. You might notice. So what I'm going to do is I'm going to expand these, make them much larger. That's this next picture here. So that blue area, I'm just blowing up that blue area. This is a teeny weeny little rectangle here, right? And this is the corresponding teeny weeny little parallelogram that comes out. And I need to know, what does this G function do? How much does it stretch out the blue area to give me the green area? Yeah, everybody good? So this is a kind of a brute force calculation. The neat thing about this calculation is it's going to combine ideas from chapter 3 with ideas from chapter 1. We're going to make derivative transformation arguments about input vectors and output vectors, and then we're going to find ourselves needing to compute the area of a parallelogram, a la chapter 1. Right? So here we go. Let's take these one at a time. Let's look at this first edge vector there. That's the edge, bottom edge of our rectangle, and it's pointing in the E1 direction, right? And I'm going to presume that this rectangle here has a width delta U and height delta V. That's where it came from, right? We took the rectangle and we did the usual chopping. So this width is delta U, that height is delta V. So this vector, then, I know the direction it's pointing. I know how long it is. I know what that vector is. It's E1 delta U. And that tells me that I know what this vector is. That vector is what you get when you apply the derivative transformation to E1 delta U. Right? Oh, I think I made a bad color choice there. Here, let me do that in orange. That is what you get when you apply the derivative transformation of G to E1 delta U. Yeah? Everybody remember the chapter 3 business, right? The derivative transformation takes input vectors and gives you output vectors. It's exactly what we're looking at here. I need to know this output vector. Okay, derivative transformation times input vector. Okay, now let's look at this. Oh, I keep with the wrong color. Let's look at this thing here. We have a scalar, delta U. It's going to factor out. And what's left over, again, familiar. Derivative transformation acts on a standard basis vector and give you a partial derivative. You can think of that as a two-step process, if you like. Derivative transformation on a vector gives you a directional derivative. A directional derivative with velocity being a standard basis vector is a partial derivative. Okay. So, this is that. How we doing? Everybody on board? We can talk about it if you'd like. Everybody happy? Yeah.
If, for example, that square domain turns into the pointed.
Yeah. The
why doesn't the square tiny domain also turn into a pointed?
Yeah. So it's a matter of scale. So, you know how? Let's see. What would be a good analogy? Linear approximations do a really good job on the small scale. They do a really bad job on the large scale. And that's roughly what we're talking about here. So on the large scale, yeah, you're quite right. We've got a nice, pretty rectangle when it's turned into a curvy, lumpy, weird, pointy thing, right? The curvy, lumpy is a large scale phenomenon, right? Yeah, this edge here is curved, but it has the chance to curve because it's so long. If this is a really teeny weeny little piece, then this little teeny weeny little piece over here, it just hasn't had enough distance to be able to actually get around to curving much yet. Does that make sense? Mm-hmm. Yeah. It's kind of related to, why does the world look flat if it's actually round? Because we're looking at a very small piece of it. I did this calculation recently, by the way, because we're here at the beach. I look out into the beach, I see the horizon. I'm like, hey, how far is the horizon from here anyway? Is that 750 miles? Or is that half a mile? How do you know? It's kind of hard to tell, right? Anyway, you can draw a little Pythagorean triangle and you can figure it out. And it turns out that even if you're 200 feet in the air, the horizon, it's about 17 miles away. And standing kind of right at the beach, maybe just slightly above the waves, where your eyes are 6 feet above sea level, horizon's 3 miles away. It's just not that far, right? And the Earth has got a circumference of 24,000 miles. And so if you're looking at something at 17 miles away, it just, on the scale of 24,000 miles circumference, it just doesn't, you can't see the curvature. So that's same kind of thing here. Yeah. Okay. All right. So we were here. Yeah. Okay. So we know what this edge vector is. This edge vector here is GU du. GU delta u, if you prefer. Okay. Highly analogous calculation that I'm going to let y'all think through on your own. Be a good exercise. It's morally the same point, but this edge vector, being as it is the image of that edge vector is GV delta V. Be a nice exercise to think it through and make sure you're comfortable with why that is. Totally analogous to what we just did here. Okay, remember what our goal was. Our goal was to find this area. We just want to know how big this thing is. More specifically, I want to know this area is what stretching factor times that area. I already know this area. This area is delta U, delta V. But what is it that I multiply by delta U, delta V to compute this area, this parallelogram? Now I know the edge vectors of the parallelogram. We're back to chapter 1 business. I have edge vectors that are GU delta U, GV delta V. Here those are. GU delta U, GV delta V. Let's take those edge vectors. Make a little 2x2 determinant out of them. Thank you, chapter 1. That's the formula from chapter 1 for the area of a parallelogram in 2 dimensions. And we just have to compute this little determinant. So let's focus on the algebra down here for a moment. This algebra. So this determinant here, you multiply like that, and then you multiply by like that and subtract. Notice that each one of these factors is going to have delta U, delta V in it. right? That also has delta U, delta V in it. So I'm just going to pull out that common factor of delta U, delta V. All that's left over is this 2 by 2 determinant, which you may recognize. This matrix here is our Jacobian matrix. It's the partials of the output variables, x and y, with respect to the input variables, u and v. Coincidentally, you might say, depending on your point of view, coincidentally, arranged exactly as the Jacobian matrix is arranged. That's exactly the Jacobian matrix. What are the odds? And notice that we are in fact done then. We were interested in finding, what is the area of this output parallelogram? How much does that get stretched out from the area of the input rectangle, which of course is what delta U, delta V was. And that stretching factor, that area stretching factor, here it is. It's the absolute value of the determinant of the Jacobian matrix of your function. Everybody on board? So we're kind of done. We know how to do change of variables now in 2 dimensions. Change of variables is done by the following idea. View your domain as being the image of something. Plug everything in to rewrite everything in terms of the new domain variables. Don't forget to pay the price. You got to insert your stretching factor, your area stretching factor. And then celebrate. You now have an integral on a new domain. Hopefully, much easier then. Okay. So so this gets written down here. There it is. Let's see what we just did here. So view your undesirable domain as being the image. I guess I kind of wrote this equation sort of cosmetically backwards. View that undesirable domain as being the image of a better domain, more desirable domain. Plug in that, look, x and y are functions of u and v. So, you plug in, rewrite everything in terms of u and v because, well, that's just, of course, right? You pay the one cost. Don't forget to include your stretching factor. That says how much do you have to multiply the area of the rectangle in the pullback domain to get the area of the parallelogram in the new domain, and you're good to go. Stretching factor is the big point. Okay. All right. Let's see some examples. All right. Okay. So let me not get ahead of myself here. So we'll start off with this integral here. Looking at this is an integral on this domain that I've got drawn here. This is a very strange shaped domain. How am I going to tell you what this domain is? I want to come at this change of variables business sort of in small stages. So this first example, I'm going to explicitly give you the undesirable starting domain as being an image. Right there in the statement of the question, I'm going to say your undesirable domain that you hate is the image by way of a given function g of a nice pretty little square. So here that is. Our undesirable domain is the image by way of this function of the unit square. So unit square in the domain, ugly domain there in the target. Okay, so G is given. Everybody see what we're talking about? Okay. So let's do a pullback. The question is to consider this integral right here, looking at an integral of x plus y defined on this domain. And let's take a moment to recognize what a horrifying inconvenience that's going to be. This one's not I guess horrifying is an overstatement. But this is going to be inconvenient because no matter how you slice up this undesirable domain, you are going to slice through corners. You're going to slice through that corner and this corner, or similarly if you do it the other way. Okay. So we're going to do a pullback. I already know that this is an image. I already know my new domain. All I've got to do is plug into the formula. The formula says rewrite everything and don't forget your stretching factor. Your stretching factor is the Jacobian determinant. Right? Now we do have to find the Jacobian of this function. So here we go. X and Y are functions of u and v like that. And you got to take the appropriate partial derivatives. So, all right, here we go. The u partials are 2u and 3. There we go. Those are the u partials. The v partials of x and y are 3 and 2v. There it goes. Right, so it's the same Jacobian matrix that we did back in chapter 4, talking about representative of the derivative transformation. Write that Jacobian down. The determinant gives us our stretching factor, and there it is. Now, this is something undesirable about this expression. Of course, we don't like this expression because it's got an absolute value in it. Now, this is a serious problem. Absolute values. We don't have any convenient integral rules that when there's absolute values in there, right? The power rule doesn't work if there's absolute values in there, etc. Right? So we've got to figure out how to get rid of these absolute values one way or the other. And let's. I'll talk about how to do that. I claim that there is a visually convenient demonstration of what to do, how to deal with this absolute value. In fact, right here on the page, the picture of what to do is right here. This tells me right there that u is always between 0 and 1. Anybody see that? It also tells me right here that v is always between 0 and 1. And if u and v are always between 0 and 1, that's never bigger than 4. And therefore, this is never greater than -5. Therefore, it's always negative. And the absolute value of a negative is the negative of that thing. Everybody on board? By the way, I may have said a word or two about this at the start of the course, but absolute values and inequalities and this kind of stuff is, the algebra of inequalities, the algebra of absolute values, and the like, gets swept under the rug very often in high school classes, and a lot of students have been implicitly sort of it's been condoned to just kind of, if you see absolute values, just throw them away. They'll count off 1 point and go about your business, right? And that's a terrible precedent that some high schools set. It's absolutely inappropriate. It does not work. It's wildly wrong. And there is algebra, ways to understand absolute values and inequalities and this kind of thing. So that's something that we have to start taking seriously. If you are uncomfortable with this step here, let's talk about it in office hours this afternoon. And likewise, if you run into trouble with algebra of inequalities, let's talk about it in office hours. But that's it's not a triviality that can be ignored. Okay, so there's our stretching factor. It's all downhill from here. Our original integral was this. First thing I need to do is rewrite x and y in terms of u and v. Now, let me point out how easy that is. X and y in terms of u and v, they're given right there. Right. So, for example, x is, you can see right there, u squared plus 3v. It says in the g function how to rewrite x in terms of u and v. Okay. Likewise, y is v squared plus 3u. So again, that's just plugging in. No tricky curves there. Okay. Having done that plug in, don't forget to stick in your stretching factor. This again is the the cost that we pay for the luxury of being able to change our domain. There's our stretching factor. That allows us to turn a dx dy integral on our highly undesirable R domain into a du dv integral on our much more desirable D domain. We like that D domain because D has bounds 0 to 1, 0 to 1, right? It's the unit square. And so this, nightmare of an integral here turns into this much nicer integral here. So it's polynomial. Right. Now, I confess, the integrand was nicer here. X plus y. Lovely. Right? Well, that's not going to last long as a consolation because of how ugly the domain is. Furthermore, the domain was curvy. It had curved edges, which means that in the bounds of the inside integral, this innocent-looking thing here, in the bounds of the inside integral, you're going to have nasty functions. Right? So the outside integral that you would evaluate here, still ugly. Right? So this is much more desirable, no question. Everybody on board? Okay, next example. How do we? I'm sorry. Break time. This is a great place to take a break. We will pick up here at let's say 11:17. Okay. See you in a minute.